lecture. AK, these are the discrete time Fourier series coefficients. They are periodic, and this is AK plus Rn. So Rn is in the subscript. It's not over here, it's in the subscript. Okay. 10th property is convolution. So if x of n has a Fourier series, has the Fourier transform x of ej omega, and y of n has a Fourier transform y of ej omega, or maybe I write h. This is h to be consistent with the continuous time Fourier series. Convolution is for LTI systems. LTI systems. So y of n, which is a convolution of x of n and h of n. This is aperiodic convolution. Aperiodic convolution. This is equal to y of, this is y of ej omega, which is equal to x of ej omega into h of ej omega. I'm not going to do a proof because it's the same, exactly the same one as for the continuous time Fourier transform. This exists if h of n, if LTI system is stable, if LTI system is stable, which implies summation n h m is less than infinity. If this is not the case, if this is not the case, this is not the case, then if it's not the case, then need to use Z transform. Property number 11 is accumulation, which is the same as integration. So in accumulation, x of n has a Fourier transform x of ej omega. Y of n is k is equal to minus infinity to n x of k, and if you recall, this is the running sum, which was the running integral in the case of the continuous time Fourier transform. So the Fourier transform here is y of ej omega. And what is this Fourier transform? So if you recall from the continuous time Fourier series case, k is equal to minus infinity to n x of k is simply the convolution of x of n and u of n, where u of n is simply this thing. This is u of n. When you do u of n minus k, so u of n minus k would be, u of n minus k would be, this would be k. This would be 0, this would be minus 1, like this here. And since it's u of n minus k, this would be n, this would be n minus 1 and so on and so forth. So you would be summing from minus infinity all the way up to n. So that's why you have this n, which corresponds to this n over here. So if I take the Fourier transform of y of n, so the Fourier transform of y of n is simply x of ej omega into the Fourier transform of u, which is u of n, which is u of ej omega, which is simply equal to x of ej omega into pi k delta omega minus 2 pi k plus 1 over 1 minus e minus j omega, or this is equal to pi x e j 0 summation k equals minus infinity to plus infinity delta of omega minus 2 pi k plus x of e j omega divided by 1 minus e minus j omega. And this part over here corresponds to because of DC or average value. Okay. Let me do an example on convolution. H of n is alpha n u n, where alpha, absolute value of alpha is less than 1. X of n is beta n u n, beta is less than 1, and alpha is not equal to beta. So y of ej omega, or maybe I start from x. H of ej omega is 1 over 1 minus alpha e minus j omega, and x of ej omega is 1 over 1 minus beta into e minus j omega, and y of ej omega, which is the product, is h of ej omega into x of ej omega is simply 1 over 1 minus alpha e minus j omega into 1 minus beta e minus j omega, which I can write as a over 1 minus alpha e minus j omega solved by partial fraction expansion plus beta over 1 minus beta into e minus j omega, or 1 equals a into 1 minus beta e minus j omega plus b into 1 minus alpha e minus j omega. Let e minus j omega equals 1 over beta. So 1 is equal to, so when I put 1 over beta over here, so this will be 1 minus 1. So this is equal to 0, or 1 is equal to beta, b into 1 minus alpha over beta. This implies b is equal to minus beta over alpha minus beta. And if e minus j omega is equal to 1 over alpha, 1 is equal to a. So when I put alpha over here, this is 1. So 1 minus 1 is 0. So a into 1 minus beta over alpha. This implies a is equal to alpha over alpha minus beta. Or y of ej omega equals 1 over alpha minus beta into alpha over 1 minus alpha e minus j omega minus beta into 1 minus beta e minus j omega. Or if I take the Fourier transform here, I take the Fourier transform here, I'll get y of n equals 1 over alpha minus beta. This would be alpha n. This is alpha n into 1. So this is alpha n plus 1 minus beta. This is beta of n u n. So this is beta n plus 1, this whole u of n. Okay. What happens? What happens if alpha is equal to beta? So if alpha is equal to beta, y of ej omega is simply 1 over 1 minus e minus 1 minus alpha into e minus j omega whole square. And if I take the Fourier transform, then from the previous lecture, y of m equal, using the differentiation property, this is simply alpha, this is n plus 1, this is n plus 1 into alpha n u of n. Okay, good. How about another example? So this is a system model. This is ej n pi w1 of n, ideal low pass filter with a cutoff of pi by 4, w2n ejn pi same ideal low pass filter, ideal low pass filter, WC is pi by 4, and this should be like this, pi minus omega c, 0 plus omega c. The side is 1. And then this one goes over here. And this is some y of n. This is x of n. So we want to see, okay, what is this? So what is the above system equivalent to? Okay. So we know W1 of n equals ejn pi into x of n. So this is being frequency shifted. So if I write the Fourier transform, W1 of ej omega is simply x of ej omega minus pi. Okay, so this is being frequency shifting property. W2 of n, or W, maybe I switch to the frequency domain now. So switch to omega domain. So W2 of ej omega is simply W1 of ej omega into ej, is W1 of ej omega minus pi, right? So this is again frequency shifting property because W2 of n is ej n pi into W1 of n. So W2, which is equal to, so if I replace omega by omega minus pi in here, I'll get this is equal to x of ej omega minus 2 pi, but this should be equal to x of, no, no, this is not right. Wait. Sorry. We've forgotten about the filter. Where's the filter? Okay. So when we switch to the omega domain, W2 of Ej omega is simply W1 of Ej omega into H low pass of Ej omega, which is equal to X of Ej omega minus pi into H low pass Ej omega. Ej omega, which is equal to, okay, so this is W2 of Ej omega. What is W3n? W3n is Ejn pi into W2n. So when I take the Fourier transform here, W3 of Ej omega is simply W2 of Ej omega minus pi. Frequency shifting property again over here. Or W3 of Ej omega is simply, so omega minus pi I replace over here and I replace over here. So I'll get X of Ej omega minus 2 pi into H low pass Ej omega minus pi. This becomes a high pass filter. This is a high pass filter. And this one is, since it's periodic, it's repeat. So this is equal to X of Ej omega. So W of 3 Ej omega is simply X of Ej omega into H high pass Ej omega. Okay. And what is W4 of Ej omega? And W4 of Ej omega is simply X of Ej omega into H low pass of Ej omega, or this implies Y of Ej omega, which is equal to W3 of Ej omega plus W4 of Ej omega is simply X of Ej omega into H low pass of Ej omega plus H high pass of Ej omega. And what is H low pass plus H high pass? This is, let's call this simply H of Ej omega. So let's draw this omega H low pass Ej omega. The cutoff frequency is pi by 4, right? The cutoff frequency is pi by 4. So I have this signal over here. This is minus pi. This is plus pi. This is pi by 4. This is minus pi by 4. This is 0. This height is 1. And on top of it, I add, maybe I draw it here. I add omega H high pass Ej omega, which is centered around pi. This is pi minus pi. This is 0. This is 1. If this is pi minus pi by 4. Pi minus pi by 4, which is simply 3 pi by 4. Okay, so if I add these two, I'll get H of Ej omega, which is equal to 0. So I have from 0 to pi by 4. 0 to pi by 4 is this portion, and then 3 pi by 4 to pi is this one. 3 pi by 4 to pi is this one. So this is pi. This is 3 pi by 4. This is pi by 4. And obviously I have the same thing over here. This is minus pi, minus 3 pi by 4, and minus pi by 4. Maybe I move the 0 over here. 0 is over here, the site is 1, and this is an ideal band stop filter because it's stopping these frequencies. This is an ideal band stop filter. So this is how you actually do analysis using convolution and using the property of convolution. Okay. The 12th property is the multiplication property, right? This is the 12th property. Yeah. So the 12th property is the multiplication property, which is identical to the continuous time Fourier transform case. It's the multiplication property, and I'm not going to prove it, but the only difference, which I'll tell you, multiplication property, y, so maybe we'll start with x. X of n has a Fourier transform x1 of ej omega. X2 of m has a Fourier transform x2 of ej omega, and y of n, which is equal to x1 of n into x2 of n, has a Fourier transform y of ej omega equals, and let me recall the continuous time Fourier transform case. In the continuous time Fourier transform case, x1 of n multiplied by x2 of n had a Fourier transform 1 over 2 pi minus infinity to infinity x1 of j omega into x2 of j into omega minus theta d theta. And this was a periodic convolution. This was a periodic convolution. Why? Because these are aperiodic. These are aperiodic. And that's why this summation is from minus infinity to infinity. However, in our case now, this is 1 over 2 pi. So you can go home and derive exactly on the same steps as for the continuous time Fourier transform case. This is over 2 pi. This is x1 of ej. I'm sorry, this should be theta. Sorry, this should be theta tau t minus tau d tau. So this should be ex1 of ej theta into x2 of ej omega minus theta d theta. These are periodic. So this is an example of periodic convolution. So that's the difference between the continuous time and the discrete time Fourier transform case. When you multiply in the time domain or in the n domain, the convolution is either aperiodic, or it's periodic. Maybe I'll rewrite this one over here. This one is a periodic convolution. Okay, good. So what we can do is we can convert periodic convolution into aperiodic convolution to make life easy. Convert periodic convolution into aperiodic convolution. And how do we do that? You choose theta to be between minus pi and plus pi, then y of ej omega, which is equal to 1 over 2 pi from minus pi to plus pi x1 of ej theta. So this is only a 2 pi interval, x2 of ej omega minus theta d theta. Okay. Define x1 of ej omega, x1 hat of ej omega to be equal to x1 of ej omega over minus pi to plus pi and 0 else. So this implies y of ej omega is simply 1 over 2 pi minus pi to plus pi x1 hat of ej theta into x2 of ej omega minus theta d theta. Or this is equal to, since this one is 0 outside minus pi, so this becomes 1 over 2 pi, this function. So this becomes 1 over 2 pi minus infinity to plus infinity x1 hat ej theta x2 ej omega minus theta d. So this is a periodic convolution. This is a periodic convolution of x1 hat ej omega and periodic x2 of ej omega. Okay, let me do an example. And before I do an example, let me find if this is h of ej omega. It's an ideal low pass filter. This is minus omega c 0 plus omega c omega pi minus pi 1. So this is an ideal low pass filter. So what is h of n? What is h of n? So h of n is 1 over 2 pi minus omega c plus omega c, h of which is 1 into e plus j omega n d omega, which is equal to 1 over 2 pi e plus j omega n over j n minus omega c to plus omega c, which is equal to e plus j omega c n minus e minus j omega c n over j2 and 1 over n pi. And what is this thing? This thing by Euler's identity, this thing is simply sine. So this implies h of n is sine n omega c divided by n pi. This is non-causal and oscillatory. Okay. So we are going to use this result. That's why I proved this one. So let's say we have x1 of n is sine n pi by 2 over n pi, and x2 of is equal to sine n 3 pi by 4 over n. Okay. And we want to take the Fourier transform. So obviously this is an ideal low pass filter with omega c equals pi by 2. This is an ideal low pass filter with omega c equals 3 pi by 4. Okay, so let me sketch this. Let me sketch this here. Pi by 4, pi by 2, 3 pi by 4, pi. So 0, pi by 4, pi by 2, 3 pi by 4, pi, 5 pi by 4, 6 pi by 4, 7 pi by 4, 8 pi by 4, minus pi by 4, minus 2 pi by 4, minus 3 pi by 4, minus pi, minus 6, minus 7, and minus 8. Okay. This is, and what I want to do is let me copy this one. I don't want to draw again. Okay, let me move this here. Okay, let me draw this with the green one. So 0, pi by 4, pi by 2, 0, pi by 4, pi by 2. So this is 0, this is pi by 2, this is minus pi by 2. This is x1 of ej theta. Let me rename this to theta, because this is what convolution does. You relabel the axis, so this is also theta, and maybe this one I'll just choose black here. So this is theta, and then this is 0, pi by 4, 0, pi by 4, pi by 2, 3 pi by 4, 0, pi by 4, pi by 2, 3 pi by 4, pi by 4, 2 pi by 4, 3 pi by 4, and pi by 4, pi by 2, 3 pi by 4. Height is 1, so we don't care about the height. So this is 0, this is 3 pi by 4. So each division is pi by 4. Okay, and this is minus 3 pi by 4. And this will repeat at 2 pi. So since this repeats at 2 pi, so this would be 2 pi, 2 pi, 2 pi minus 3 pi by 4, which is 8 pi, 5 pi by 4. So 3, 4, 5. 5, 6, 7, 8. This is 2 pi, and 4, 5, 5, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and there is an eighth one over here too, minus 2 pi. 3, 4, 5, 6, 7, 8. Okay. Now what we want to do is, this is x2 of ej theta, or maybe no, this is x2 of ej omega minus theta, where omega is 0, where omega right now is 0. So if omega is equal to 0, and let me select this one. Let me select this one. And I'm going to move this thing. I'm going to move this thing on top of this one. So when I move this thing on top of this one, maybe I will do it here. If I move this thing on top of this one, what is the overlap? The overlap is this one. So the overlap is, let me see. So the overlap is this one, this one, this one, and this one. So there are four pi by 4 divisions that are overlapping. So if this is the case, so let me get rid of all these. So at omega is equal to 2, overlap is pi, right? Okay, good. Okay. Okay. Let's select again. Again, if I move this one, and now if I move by pi by 4, 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 there is 1 overlap, 2 overlap, 3 overlap. So 1 overlap, sorry. So there is 1 overlap, 2 overlap, 3 overlap, 4 overlap. So let me so there's still 4 overlap. So this is pi. So at omega is equal to pi by 4, overlap is still pi. Okay. Let me select again. If now I move by another, now I move by another pi by 4, so now my zero, wait, pi by 4 division. This was pi by 4 division. And let me get rid of this x2 over here. Get rid of this pi, 0, pi, minus pi. Get rid of this one. And let me write here. Let me write, this is 0, this is pi by 4, this is pi by 2, this is 3 pi by 4, this is minus pi by 4, this is minus pi by 2. So what we want to do here is, now we want to shift by, so this is actually pi by 4, wait, this is pi by 4 or pi by 4, that's fine. Now if I shift by another, by 2 pi by 4, which is equal to pi by 2, so it means my 0 has to be on top of this pi. So let's see what happens. So if my 0 is on top of this pi, so if my 0 If my 0 is on top of this pi, I have only 1, 2, 3 overlappings. There I have 1, 2, 3 overlapping. And let me bring this down here. So at overlap is 3 pi by 4. Overlap is pi, overlap is pi, and overlap is pi. Okay, good. If I shift by 3 pi by 4 and finally pi, overlap is, and if I shift by 4 pi by 4, which is pi, overlap is, so let's see. So if I shift by 3 pi by 4, so if I shift this by 3 pi by 4, which means my 0 is now on top of 3 pi by 4. So 0 is on top of 3 pi by 4. So if 0 is actually only 2 overlappings. I think it's not aligned properly. Now it's aligned. So I have 1 and 2. This is still not overlapping. So there are only 2 overlappings. So let me bring this down here. So there are only 2 overlappings. So there are only 2 pi by 4s that are overlapping. So overlapping is, so maybe I write it like this. Maybe I write it like this. There is 4 times pi by 4, which is equal to pi. Again, I have 4 divisions of pi by 4, which is pi. And here I had 3 divisions of pi by 4, which is 3 pi by 4. And here I had 2 divisions of pi by 4, which is pi by 2. What about the last one? So last one, because this, if whether I shift to the left or right, so this is plus minus, plus minus, plus minus, plus minus, because this is symmetrical. So this is symmetrical. Okay, so for the last one, so again, if I pick this one and I shift it, so now my 0 is going to be at pi. So 3 pi by 4, this is pi. So if my 0 is going to be at pi, so if my 0 is at pi, wait, doesn't make sense here. Let me write pi here too. This is pi. This is pi. So now if my 0 is at pi, so now my 0 is at pi. So there is this one that is overlapping. There is this one that is overlapping. And there is this part that is overlapping. So there are 2 parts again that are overlapping. So let me bring it down here. So there are 2 parts of pi by 4 that are overlapping. So this is pi by 2. Now remember that there is a 1 over 2 pi here. So there is a 1 over 2 pi here. So everything is divided by 2 pi. So if everything is divided by 2 pi, so my answer is going to be, so let me sketch this one. So this is omega. This is y of ej omega. So let me again draw it like this. So ruler and 0, pi by 4, pi by 2, 3 pi by 4, 0, pi by 4, pi by 2, 2 pi by 4, 3 pi by 4, and pi. 0, pi by 4, pi by 2, 3 pi by 4, and pi. So this is going to repeat. So 0, pi by 4, pi by 2, 3 pi by 4, and pi. This is omega. This is minus pi by 4, minus 2 pi by 4, minus 3 pi by 4, and minus pi. Okay, and let me draw a ruler over here too. So ruler over here. And then this is, or maybe I need this ruler again. So this is, let's say this is pi by 2. So 0, this is pi by 2. So this is pi by 2, and this is pi by 4. Okay. So this is pi by 4, this is pi by 2. Okay. So this one, so this is half, or 1 by 4. This is 1 by 4, and this is half. Okay, this is half. So everything here is divided by, these results are divided by 2 pi, because there is a 1 over 2 pi in the integral. Because there is a 1 over 2 pi in the integral, because there's a 1 over 2 pi in the integral, so everything is divided by 1 over 2 pi. So this becomes half. So half, half. So up to pi by 4, we have a half. So half here and half here. Okay, and then 3 pi by 4, this is a linear decrease, and 3 pi by 4 pi you have 1 over 4. 3 pi by 4 pi you have 1 over 4. 3 pi by 4 pi you have 1 over 4. So this is connected like this. This is connected like this. And then this is constant at half, 1 by 4, sorry. This is constant. This is constant at 1 by 4. And then obviously this repeats. This repeats. This repeats. So this is how you find the periodic convolution. You convert the periodic convolution into aperiodic convolution and then solve it. Okay, good. Property 13 is on duality, and this is the last property of the discrete time Fourier transform. We know from continuous time, for continuous time Fourier transform, x of t is 1 over 2 pi minus infinity to infinity x of j omega e plus j omega t d omega, and we know x of j omega is minus infinity to infinity x of t e minus j omega t dt. Now this t and this omega both are continuous. They are continuous. This x and this x, they are they are aperiodic. Sorry, this x and this x, they are aperiodic. So if I can, so if I take this 2 pi on this side, so maybe I rewrite it and I say this is 2 pi equals this one. Then this t and omega are same. This omega is this t is this omega, and the only difference is in the sign of the exponent. This is the only difference. So this is the delta. This is the delta. The delta is the sign of the exponent, sign of exponent. So we said if x of t has a Fourier transform x of j omega, then x of t has a Fourier transform 2 pi x minus omega. So we said, okay, you multiply x of t by 2 pi, interchange omega and t, and this is possible because both are continuous variables, and finally replace omega by minus omega. Unfortunately, the discrete time Fourier transform does not have a dual. The inverse Fourier transform and the direct Fourier transform and the Fourier transform for the discrete time case, they are not duals of each other. However, note this. For the continuous time Fourier series, we have x of t equals, and same is the case for the continuous time Fourier series case, k is equal to minus infinity to plus infinity, ak e plus j k omega naught t, ak equals 1 over t x of t e minus j k omega naught t dt. This is for the continuous time Fourier series. For the discrete time Fourier transform, we have x of n equals 1 over 2 pi x of ej omega into e plus j omega t omega n, sorry, plus j omega n into d omega, and finally x of ej omega equals minus infinity to plus infinity x of n e minus, and this is not a integral, this is a sum, n is equal to minus infinity to plus infinity e minus j omega. This t is continuous. This omega is continuous. This k is discrete. This n is discrete. So in this equation, if I compare these two equations, t equals 2 pi. So this is the first thing. T equals 2 pi. T equals 2 pi. So integral of t is the same as integral over 2 pi. This t is continuous. This omega is continuous. This is t. This is omega. Omega naught over here is 2 pi over t, but t is equal to 2 pi. So this implies omega naught equals 1. So this is 1. This is equal to 1. And similarly, this is equal to 1. So the only difference left now is this k and this n. This t and this omega. So discrete k, discrete n, continuous t, continuous omega. Same is the case here. This t and this omega, this k and this n, both discrete. So the only difference in both the equation is this is plus, this is minus, this is plus, this is minus. So what we need to do is, so we will, the first thing is t equals 2 pi. T equals 2 pi. Interchange t and omega. And the third one is interchange n and minus k, or interchange n and k and then replace k by minus k. Maybe this is what we do. Interchange n and k, and maybe the fourth one, replace k by minus k. So this is continuous variables, discrete variables, and then replace, just like we did omega by minus omega, replace k by minus k. Let's look at an example. So we want to find x, the Fourier transform of x of ej omega, where x of n is sine n pi by 2 over n pi. We know, okay, this is an ideal, we know this is an ideal low pass filter with omega c equals pi by 2. So the procedure is, look at the continuous time Fourier series pair. Do we know a continuous time Fourier series pair that has this form? So look for a continuous time Fourier series pair that has this form. And we know that. So let's look at the square pulse train. So square pulse train. So for a square pulse train, we had this thing. We had minus t1, 0 plus t1. Then we had this one again at t, and we had this one again at minus t. This goes on here, this goes on here. This is not, it's a little fat. This is probably all right. And this is some t by 2. This is some minus t by 2. This is 1. This is t. This is x of t. So x of t was 1 for t less than absolute value of plus minus t1, and 0 for t1 less than t less than equal to t by 2. Right? So recall this was x of t, and what was ak? So the Fourier series here, so ak were 2t1 sine omega t1 over omega, no, this was not omega t1, this was k omega naught t1. So this was k omega naught t1, and this was k omega naught t. I don't think so there was a t1 here, so this was 2t1. This was only 2. This was 2 sine k omega naught t1 over k omega naught t when k is not equal to 0, and this was 2t1 divided by 2t1 divided by t when k is equal to 0. So this is the average value. Okay. So 2 sine k omega naught t1 divided by k omega naught t. This is equal to omega naught is equal to 1, t is equal to 2 pi. So this 2 cancels with this 2. Omega naught is equal to 1. So I have sine kt1 divided by pi k. So I have used t is equal to 2 pi, which implies omega naught equals 2 pi by t, which is equal to 1. And then what I do is I interchange t and omega. So when I interchange t and omega, I get x of ej omega. So x of ej omega becomes 1 omega less than equal to t1 and 0 for t1 less than omega less than equal to pi. This is why, because t by 2 equals pi. And t1 equals, so since we are interested in finding the Fourier transform with the cutoff frequency is pi by 2. So we say t1 equals pi by 2. This is equal to pi by 2. And then I interchange uh, n and k. So if I interchange n and k, so my x of n becomes sine n nt1 over nt1, or maybe this is sine n pi by 2 over n pi by 2. This is because k is now replaced by n, or minus n, and once is the same thing, or interchange n and k, or interchange n and minus k. Maybe I do minus k here. N and minus k. So sine is odd, so this is odd, so we get the same result. Or maybe we replace interchange n and minus k, or maybe we interchange minus n and k. So it's one and the same thing. You get this one. So our result is sine n pi by 2 over n pi by 2 has a Fourier transform 1 for omega less than equal to pi by 2 and 0 for pi by 2 less than omega less than equal to pi. And if you sketch this one, this is simply like this. This is x of ej omega. Zero pi by 2 minus pi by 2. This is 1. This is pi. This is minus pi, and obviously this is periodic. This is omega, and this is periodic. Okay. What about the discrete? So we didn't look at the duality for the discrete time Fourier series case. So for the discrete time Fourier series, I need to realign this one. Let me realign this one. Okay. For the discrete time Fourier series case, we have AK equals to 1 over n, so maybe I put n over here, n over n values, x of n, e minus j k 2 pi by n, and then we had x of n equals k n values, ak e plus j k 2 pi by n over n. So k is discrete, n is discrete. This is periodic, this is periodic. So this has exactly the same relationship that we had for the continuous time Fourier transform case. So discrete time Fourier has same duality relationship, same duality. Why? Because n and k and n, this is minus, this is plus. It has same duality relationship as continuous time Fourier transform. Okay, and let's do one example. We know this is example 3 from example 3.12. From example 3.12, we know for a discrete time periodic pulse train. So we have minus n1 plus n1. This is 1. And then we had, this was 0 here, this was 0 here, this was 0 here. This is n minus n1. This is n plus n1. This is 0, this is n, this is x of n. And then we had this is minus n1, this is minus n plus n1, and then we add this periodic over here. Okay, so x of n was, so x of n was 1 for n less than equal to n1, and 0 for n1 less than n less than n2. Less than n2. Less than n2. Okay, and we know from chapter 3, we know a naught is 2n1 plus 1 over n, or maybe this is ak. This is periodic, so ak when k is equal to 0, plus minus n, and so on and so forth, and ak equals 1 over n sine 2 pi k over n into n1 plus half over sine pi k by n. This is when k is not equal to 0, not equal to plus minus n, so on and so forth. Okay. So we know this. So if x of n is 1 over 9 sine 5 pi n by 9 over sine pi n by 9, when n is not a multiple, of 9, and this is 5 over 9, when n is a multiple of 9, then use duality property property to find the discrete time Fourier series of x of n. That is a case. So to do that, we do exactly the same thing that we did for the continuous time Fourier transform case. So we know n times ak equals some n equals some n x of n e minus jk 2 pi by n or 5 by n when k equals, so here we have used, so we can, this is 5, this is n1 plus half, so this is n1 is probably equal to 2, right? So 4 plus 1, 5, and n is equal to 9. If we compare this one with this one and this one with this one, n1 is equal to 2 and n is equal to 9. So k is equal to 0 plus minus 9 and so on and so forth. And this is 1 over 9 sine 5 pi k over 9 divided by sine pi k over 9 when k is not equal to 0, k is not equal to 0 plus minus 9 so on. And this is equal to what? This is equal to this sum n equals over some 9 elements. This is 1, there is an n over here. This is n and this is ak. This is ak. So n times ak, so this n is equal to 9. So this is probably, I also write this as n, which is equal to 9. 1 for n less than 2, this is n1. And this is 0 for 2 less than n less than 4. And then with this thing, this is x of n. And with this one, we have this term multiplied, which is e minus e, this is ak, so this is e minus j k 2 pi by n into n, or it's e plus, sorry, because this is ak. If this is xn, n times ak, this is e minus, so this is e minus. So what do we do now? So we'll replace, so what we'll do is divide by n. This is the first step. So if I divide by n, this n is going to go from here, and I'll have 1 over 9 over here. So this is the first step. Second step is interchange k and n. Why interchange k and n? Because if you go back here, both k and n are discrete, so I can always interchange k and n. So if I interchange k and n, so this k will become n. Maybe I write like this. This k will become n. 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 This n will become k. This n will become k. And this n will become k. And then the final thing is, no need to change here. And then the final thing is you replace k by minus k. If you replace k by minus k, nothing changes here. minus k over here, absolute of minus k is the same. Absolute of minus k is the same as plus. It doesn't make a difference. Absolute of minus k is the same as plus. It doesn't make a difference. So this is our result. So we have, so if x of n, so if x of n, so if x of n is, no, sorry. So this will become then, this will become x of n. Let me write here. So this will become x of n, and this will become a of k. So if x of n is 5 by 9 and 1 by 9 sine 5 by n by 9 sine 5 by n by 9 divided by sine pi n by 9. This is when n is equal to 0, plus minus 9, so on and so forth. When n is not equal to 0, plus minus 9, so on and so forth. Then if I take the Fourier series, ak equals 1 over 9, ak equals 1 over 9 for k between 0 and 2, 0 and 2, sorry, k absolute is between less than equal to 0 and 2, and this is less than equal to, and this is 0 for 2 and 4. 0 for 2 less than k less than 4. So this was given. So this was given, and we found this one using duality property, and result of example 3.15. So the last topic in this chapter, is systems characterized by linear constant coefficient difference equation. So this is the counterpart for the differential equation case, where we use the continuous time Fourier transform to find the solution of the differential equation. Now we use the discrete time Fourier transform to find the solution of the difference equation. So in general, we have k is equal to 0 to n, ak y of n minus k equals k is equal to 0 to m bk x of n minus k. This is the nth order. Or if you take Fourier transform of both sides, take Fourier transform of both sides. So we'll get k is equal to 0 to n ak Fourier transform of y into n minus k equals k is equal to 0 to m bk Fourier transform of x into n minus k. So if I do that, this one by the difference, by the time shifting property, this is simply n naught. This is simply n naught. If this is the case, then this is equal to y of ej omega into e minus j omega k. by the time shifting property. Similarly, this one is equal to x of ej omega into e minus j omega k. So y of ej omega divided by x of ej omega is simply k is equal to 0 to m a bk bk e minus j omega k divided by k is equal to 0 to n ak e minus j omega k. So let's do some examples. So first order equation, y of n minus a of y of n minus 1 is equal to x of n. So if I take the Fourier transform of both sides, I have y of ej omega into 1 minus a e minus j omega equals x of ej omega. This is exactly the same as we did for the continuous time Fourier transform case. So h of ej omega, which is y of ej omega divided by x of ej omega, is simply 1 over 1 minus a e minus j omega. If I take the Fourier transform here, just like for the first order equation, for first order differential equation, the solution is this is the frequency response of LTI system. Our solution is still exponential, so h of n is simply a n u n. Okay, let's look at another example. So the second order difference equation, y of n minus 3 over 4 y of n minus 1 plus 1 over 8 y of n minus 2 is equal to 2 times x of n. So I'm not going to do all the steps. If I take the Fourier transform here, I take the Fourier transform here. So h of ej omega equals y of ej omega divided by x of ej omega. The numerator here is this portion, so this is 2 divided by, this is 1 minus 3 by 4 e minus j omega plus 1 by 8 e minus j omega square. So this is n naught here, this is n naught here, and there is n naught. There is no need of n naught there. So doing partial fractions. So partial fractions. This is actually equal to 1 minus quarter e minus j omega into 1 minus half e minus j omega. So quarter into half is 1 by 8. Minus minus plus becomes a plus. Minus quarter minus half becomes minus 3/4. So 2 over 1 minus 1 over 4 e minus j omega to 1 minus half e minus j omega equals a over 1 minus 1 over 4 e minus j omega plus b over 1 minus half e minus j omega. So again, you can maybe over here, you need to write a is less than 1, otherwise this will not exist. Okay. So 2 is equal to a into 1 minus half e minus j omega plus b into 1 minus quarter e minus j omega. So let e minus j omega equals 2. So 2 is equal to, so 2 over 2 is 1, 1 minus 1 is 0, is equal to b into 1 minus 2 by 4, which is equal to 1 minus half. So this implies b is equal to 4. B is equal to 4. And if I say e minus j omega is equal to 2, so 2 is equal to, 2 over 2 is 1, 1 minus 1 is 0, sorry, this is equal to 4. So 4 over 4 is 1, 1 minus 1 is equal to 0, so 4 over 2, so this is a into 1 minus 4 over 2, this implies 4 over 2, 2, so a is equal to minus 2. So a is equal to minus 2. So y of ej omega is simply minus 2 over 1 minus quarter e minus j omega plus 4 over 1 minus half e minus j omega. So if I take the Fourier transform here, I take the Fourier transform here, so I get y of m. I'm sorry, this is not y, this is h, I think so. What is this? This is h probably. Yeah, this is h. So this is h. Takes time. So this is h. Sorry. This is h. This is h of n. This is equal to minus 2 into 1 over 4 plus 4 into half 1 over 4 n plus 4 half n u of n. Because we know because 1 over 1 minus a e minus j omega as a Fourier transform a n u n when a is less than 1. Okay, the last example is, which is exactly the same one that we did for the continuous time Fourier transform case. What happens if x of m is 1 over 4 n u n, then y of n in then find y of n then find y of n for the previous system. Okay, so y of ej omega is simply x of ej omega into h of ej omega, which is equal to 2 over 1 minus half e minus j omega into 1 minus 1 over 4 e minus j omega whole square. Or this is equal to a over 1 minus half e minus j omega plus b over 1 minus 1 over 4 e minus j omega plus c over 1 minus 1 over 4 e minus j omega square. Or you're doing partial fractions, 2 equals a into 1 minus 1 over 4 e minus j omega square plus b into 1 minus half e minus j omega into 1 minus 1 over 4 e minus j omega plus c into 1 minus half e minus j omega. So if we say let e minus j omega equals 2, so 2 equals, here 2 over 2 is 1, here 2 over 2 is 1, so cancels. So this is a into 1 minus 2 over 4 square. So this implies a equals, so this is half 4, so a equals 8. A equals 8. And let e minus j omega equals 4. So 2 equals 4 over 4 is 1. 4 over 4 is 1. So this is c into 1 minus 4 over 2. So this implies c equals 1 minus 2. So it's minus 1. So c is equal to minus 2. C is equal to minus 2. And compare coefficients. Compare coefficients of e minus j 2 omega. So 0 equals, so this will become a over 16, a over 16 minus minus plus plus b over 8. This implies, so this is 2b, so b is equal to minus a over 2, which is equal to minus 4. Minus 4. So y of ej omega, so y of ej omega is equal to 8 over 1 minus half e minus j omega plus minus 4 over 1 minus 1 over 4 e minus j omega plus minus 2 over 1 minus 1 over 4 e minus j omega whole square. This property, this inverse Fourier transform, we have already found in the last lecture, and these are easier to find. So if I take easier to find, so if we take the Fourier transform of both sides, y of m equals 8 into half n minus 4 into 1 over 4 n minus 2 into n plus 1 into 1 over 4 n, and all this with u of n. This is all we want to cover from the discrete time Fourier transform case. The only one that is left is the discrete Fourier transform, which is actually taught in the DSP course, but we'll give you an introduction on the discrete Fourier transform. The continuous time Fourier transform is a subset of the Laplace transform, is a subset of the Laplace transform. Similarly, discrete time Fourier transform is a subset of the Z transform, which we'll do in the next lecture. Thank you.